Hello, everybody. Today, I'm going to talk about our work in a mobile robotics project in the Higher Institute for Applied Sciences and Technology in Syria as part of our fifth year coursework. We're going to talk about artificial potential field-based path planning using the virtual obstacle modification. This is presented by me, Ashraf Faraj, in collaboration with my two colleagues, Ahmed Mustafa and Ahmed Leisa, which we worked together on this project. It's also supervised by Dr. Chadi Al-Bitar and engineer Tarek Al-Saati. Now, the importance of autonomous robots, or autonomous agents in general, has grown exponentially in recent years. It's this need for agents that are autonomously capable of taking decisions in highly complex, unmodeled environments is what made the research interest in autonomous robots grow quite exponentially in recent years. So, for example, we have seen quite a great rise in the number of autonomous robots used in industrial applications. For example, moving supplies through warehouses autonomously, quickly, and efficiently. There's also a great deal of interest in using these autonomous vehicles in space exploration, as seen quite recently in many of NASA's Mars rover missions. Now, in this project, what we're trying to do is we're going to implement a modified artificial potential field algorithm in MATLAB and test it on a real eBug robot. We're going also to build an artificial model of the map using the Weber's environment, and we're also going to test this algorithm on the Weber's environment after programming it in the C programming language. In this project, we're going to use the eBug robot, which was constructed by ABFL University for educational purposes mainly. Now, this figure right here shows many of the basic parts of the eBug robot. For example, we have the Bluetooth module, which we're going to use in order to connect with MATLAB. There's also a proximity sensor, IR proximity sensor, really distributed along this ring right here. There's also a camera, CMOS camera, a lithium-ion battery, of course, and two motors, the left and right motors, with encoders. Now, the main project block diagram is as follows. We're going to implement the ABF algorithm in MATLAB and in Weebots simultaneously. In Weebots, we are going to write this algorithm in C and test it in the Weebots world environment that we constructed, which really matches the real environment that we constructed in our lab. We're also going to work on the algorithm method in MATLAB, and we're gonna then upload it using a Bluetooth module to the eBug in the real world to test its real performance. A quick introduction to path planning algorithms, and they're usually classified into three different methods. The first one is called the roadmap, in which we try to approximate the robot's free configuration space using a graph. And then we are going to plan a path on this graph of free space configurations. The second one is cell decomposition. In this case, we divide the configuration space into a grid-like representation, which some cells are occupied, which are those that intersect with obstacles. Others are actually free. This creates an approximate representation of the state space with a certain resolution. And then again, we use a graph-based planning algorithm to plan our path from start to goal. Now, the type of algorithms that we're actually interested in this kind of project is the potential field algorithms. In this case, we define potential fields associated with goals and potential fields associated with obstacles. The ones associated with the goal are actually attractive. The ones associated with obstacles are repulsive, and the robot moves under the influence of the total force, which is the sum of all of these forces. Now, this should guide the robot, in ideal cases, towards the goal while actually pushing it away from the obstacles. Now, the artificial potential field algorithm, we're going to find two types of forces. The attractive force, right here, which is given by the following equation, minus k attractive, a positive constant, multiplied by q minus q goal. Q is the current robot configuration, and q goal is the desired goal configuration. The second type of forces, which is associated with obstacles, is the repulsive force. It's given by the following equation, half of k rep, a positive constant. Rho q is the distance between the current robot configuration and the obstacle. Q obst is the point on the obstacle that is closest to the current robot configuration. Rho zero is an activation distance. at which if rho q is smaller than rho, we activate the force, and otherwise we stop the force. Now this figure right here might show an illustration of the potential field method. In this case, we see here that we have a goal, which is a global minimum. This right here is an obstacle. You can see that the potential associated with it actually has quite high values at the boundaries of the obstacle. So in ideal cases, the robot should slide down the surface towards the global minimum. However, in practice, most likely we're going to encounter local minimum points along the path, like the one shown here. In this case, the robot might get stuck in this local minimum because the sum of forces nearly approximates zero, which means that there is no motion whatsoever. This might give the robot the sense that it actually reached the goal, but it's actually stuck in this local minimum. This right here has actually sparked a lot of research in order to find methods to try to overcome this problem. One of the methods that are actually used when trapped in local minimum is actually what we call a virtual obstacle method. The idea is that we add a virtual obstacle, that is a virtual repulsive force source, in a position near the robot in order to push the robot away from the local minimum. One possible model of this virtual repulsive force is given by the following equations. Now Q external is the position of the virtual repulsive force. Q is the current robot configuration. D is an activation distance. In this case, we see that the virtual force actually increases linearly as the distance increases and then flats out when we are away from the obstacle. In general, the robot must move according to the sum of all forces, the extra forces, the repulsive forces of the obstacles, and the attractive forces of the goal. Now, this figure shows a simplified model of a differential drive mobile robot. As we said earlier, this robot has two independent motors, the left and the right motors. When we try to move the motors in certain speeds, they will cause the robot to rotate in an angular velocity omega and move in a linear velocity v. Now, we measure the robot's configuration relative to the goal configuration using the coordinates of this point right here, the midpoint between the two rear wheels axles, and its orientation relative to the required goal state. Once we have computed the components of the resulting force, Fx and Fy, that the robot must follow, we have to compute the desired forward and angular velocities using the following equations. First, we compute alpha, the angle of error, that is the angle between the direction of the force and the robot's current angle theta. We then compute the desired forward velocity using the following equation. Kv is a positive constant. This right here is the magnitude of the force, and cosine alpha would have to be the projection of the force line onto the robot's forward motion direction. Omega right here would have to be a constant kW, a positive constant multiplied by alpha, which is the angular error. Now, after computing these desired forward and angular velocities, we retrieve the left and right wheel velocity using the following equations. Now, another really important topic that we must address is that the robot's configuration must be updated at each time step using the motor encoder readings and the previous state. This can be done using the following equations, which are called odometry update equations. Now, theta nu, x nu, and y nu are the updated robot configuration. Theta old, x old, and y old are the robot's earlier configuration as the previous time step. R is the wheel radius, L is the distance between the two wheels, delta SL and delta SR are the changes in the encoder readings of the left and right wheels, respectively. Now to the practical results. This figure right here shows the model of the environment in Weebots. This right here is the EBAC robot. This is the obstacle that we use a rectangular obstacle to test our algorithms. The algorithm that we implemented is actually comprised of many steps. This figure right here shows the basic steps of the algorithm. First of all, we receive the previous position and the encoder readings to update the robot's configuration. Once we have the new configuration, we compute the distance from the obstacles in order to compute the repulsive forces. We also compute the attractive force using an equation demonstrated in previous slides. We further test whether we are trapped in a local minima or not by keeping track of 30 last positions of the robot in a sliding window. We test the standard deviation of this position of windows to see whether it's actually smaller than a given threshold. If that's the case, then this might indicate that the robot's positions have been quite cluttered in the last 30 time steps, indicating that the robot might be trapped in a local minima. Once that condition is satisfied, we add a virtual obstacle, which will give us an extra force component that is added to the resultant force, which is then used to compute the left and right wheel velocities using equations presented earlier. This chart here shows the epoch interface in the MATLAB program, which we actually use to upload a controller. This chart here shows the communication channel and sampling rate specification. We use actually a Bluetooth channel to communicate with the epoch robot. This here shows the controller file that we're going to use, which we implemented the algorithm. This spot shows the wheel velocities and the current configuration of the robot. And here shows the robot's trajectory when moving in the real world. The two figures here show the practical results of our controllers. Now in figure 9, we have tuned the parameters in order to avoid the obstacle without falling in any type of local minima. It can be seen that the robot starts from a start configuration, then makes a turn right here to avoid the obstacle and reaches a goal configuration. In the second case, we tune the parameters in order to fall in a local minimum, in which case we see that the positions are quite cluttered since the resultant force magnitude is quite small, which means that the robot does not know in which direction to move. To solve this, this is a figure showing how we added the virtual obstacle modification. So what happens is that the robot starts at a certain position, is trapped in a local minima. This is detected by the algorithm using the standard deviation test, and then a virtual obstacle is added at the mean point of the position windows that we were keeping track of. This virtual obstacle helps push the robot out of the local minima and towards its final goal position. So this right here concludes our project. So in this project, we studied the virtual obstacle algorithm and implemented it in the WeBots environment in C and in MATLAB. We also verified the algorithm in practice by cross-compilation in the MATLAB software with the real epoch robot. And that's it. Thank you very much for listening.